One, go, and let's go. Hello and welcome back to Calculus 3, section 14.2 on calculus of vector-valued functions. So, vector-valued function is just a vector that consists of three functions in it, one for x, one for y, and one for z. And now we are going to apply calculus to it, mainly the limit, derivative, and integral. So if you are applying limit, t goes to, I'll put just a, t goes to a of f of t, g of t, h of t, you will get the vector of limits. So whatever answer you get for each one of these will go in here. So you just do it component-wise. And that would be limits. So limit t goes to 0 for 1 plus 3t e to the t 1 over square root of t plus 1 is 1, 1, 1. Because 1 plus 3 times 0, that's 1. E to the 0 is 1. And 1 divided by 1 is 1. So they're all ones. Now, more interesting and more important than all of this is the derivative of vector-valued function, which will give us eventually the tangent vector. And that's the one that we are going to use a lot, the tangent vector. So make sure you know this one. Derivative. It's the same deal. We take the derivative in respect to t of r of t, and what we get is f prime of t, g prime of t, h prime of t. So that's what we have as our derivative. And we call this one r prime of t. So that will be the notation, r prime of t. So if I have r of t, say t squared plus 8 e to the 3t, and let's say 1 over t, the r prime of t, which is the derivative, would be 2t, 3e to the 3t, and negative 1 over t squared. So you are taking three independent calculus 1 derivatives, as you know and like, right, from Calc 1. Nothing special. Helix. Let's say you have a helix given by r of t is equal to t squared sine 2 sine t, 2 cosine t. Tell me what the r prime of t is. 2t, 2 cosine t. Yes. Negative 2 sine t. Nice. So we are going to take derivative of each one of these independently and have them right, separated by commas. If you want to use IJK component notation, be my guest. It's all good. You can. Now we are interested in, and I'm gonna put this title in blood over here, unit tangent vector. T hat. So that's our big topic over here. We know that when we take the derivative of the function, we get the derivative function, which we can use to calculate the slopes, right? And those slopes are slopes of the tangent lines. So now it makes sense to define the unit tangent vector as r prime of t divided by the magnitude of r prime of t. If you remember, the unit vector u was vector u divided by the magnitude of u, right? Do we all remember that? So we are using now vector r to get the tangent vector t. So find t hat for r three cosine t, 3 sine t, and let's say 9. So we first find r prime, which would be negative 3 sine t, 3 cosine t, 0. And then the magnitude of r prime would be, when we square all of this, we get 9 sine squared t plus 9 cosine squared t plus 0 squared. No one cares. I don't need the vector. You factor out 9, and the square root of 9 is 3. Sine squared plus cosine squared is 1, right? So it's just 3. So t hat, you will be calculating this, and then you will be taking the derivative of that to get to the normal vector eventually. So yeah. So now we have negative 3 sine t, 3 cosine t, 0 divided by t by 3, and the t hat is negative sine t, cosine t, and 0. Now you can check that this is unit tangent vector by working on its magnitude, and you see that sine squared plus cosine squared plus 0 squared is 1, right? So magnitude is 1, so this is unit vector, which is why it has a hat, not an arrow, right? We said unit vectors will have hats and regular vectors will have arrows. So, I mean, you are not wrong to put the I, j, k vectors with arrows, but it's better if you use hats because we know they are unit vectors, I, j, k. I mean, you can't go wrong with using an arrow. It's just, you know, hat is for unit vectors, so why not? All of the derivative rules for these guys are the same as calculus 1 derivatives, right? Derivative of a constant vector is 0. There's no change. And then you can work linearization in a constant multiple and all of that stuff. So the unit vector, unit tangent vector, will give you the direction of the tangent line to the curve. See, when you are in space, you have some kind of space curve of some whatever. There is a tangent line at the curvature. This tangent line has that third-dimensional slope, which we call v, right, in our straight line. So this unit tangent vector t is going to be that v for the tangent line to your space curves. So if I ask you to find the tangent line to the space curve, you guys will be computing the vector t, and then you will be using that as your vector v direction vector, right, for your, and then I will be asking you to compute that at the point. Let's see if we can find a problem. Tangent vector at the point. Great. So they have this helix given at cosine 2t for sine 3 sine 2t, and t is pi over 2. So r prime is going to be negative 2 sine 2t, 0, and 6 cosine t. Cosine 2t. Magnitude would be square root of 4 sine squared 2t plus 36 cosine squared 2t which gives us the unit tangent vector as negative 2 sine 2t, comma 0, comma 6 cosine 2t, divided by square root of 4 sine squared 2t plus 36 cosine squared 2t. So this is my unit tangent vector. Now, to calculate the tangent line, I need to find v, because, okay, tangent line at t equals pi over 2. That's given to us in a problem. So to find vector v, I need to compute my tangent vector at pi over 2. So that's going to be negative 2 sine of pi, 0, 6 cosine pi, divided by square root of 4 sine squared pi plus 36 cosine squared pi. Vector v is going to be given by, so in the numerator, sine of pi is 0, so I have 0, 0, 6. In denominator, I have a square root of sine of pi is 0, 0 squared is 0, 4 times 0 is 0, so the whole thing dies. Cosine of pi is 1, so all I have is 36, so the whole thing is 0, 0, 1. Now, to calculate the point at which we are getting all of this, we have our r calculated at pi over 2. So that's going to be, what was my cosine of pi, and then 4, and then 3 sine pi, which gives me the vector 1, 4, 0, which has a terminal point for the location 1, 4, 0. So to find my tangent line in space, I have my 1, 4, 0 point, and then plus 0t plus 0t plus 1t. So the line, tangent line, is given by the vector 1, 4, and t. 1/4t is the tangent line. So what kind of line did I get? Well, I told you, you have a space curve, some kind of space curve, and let's say this is where t equals pi over 2 is, like a 1.5 seconds almost. So the tangent line in there, the equation of this straight line is given by the vector valued function. So this is our tangent line. I was going to spell it out. Tangent line at t equals pi over 2. You change this pi over 2 to pi over 3, which is a different moment in time. The entire calculation changes. You get a different line because you are no longer at the space curve where you were before. Now it's a different location. So again, derivatives, just like limits, taken one at a time. The last one is integration. So if I need to integrate my vector r of t dt, I will get the antiderivative plus the vector of all constants. Those of you who took Calc 1, Calc 2 with me know that I always say it's either plus c or minus 1. Well, now it's plus c or minus 3 because each one of the coordinates has its own plus c. So this vector c over here is a vector c1, c2, c3 for each of the vectors. And your vector r is the integral of f of t dt, comma, integral of gt dt, integral of h t dt. Take the limits component-wise, take the derivatives component-wise, take the integration component-wise. You are doing 3 Calculus 1 problems independently and just dump them all into the vector. So integrate r of t 3 cosine 4t e to the 6t and 1 over t. So let's say this is your problem. We will say integrate and then 3 cosine 4t, comma, e to the 6t, comma, 1 over t dt. Remember, we are going to do this component-wise. What's the integral of cosine 4t? Very good. So we have 3/4 sine 4t e to the 6t over 6. And what's the integral of 1 over t? Very good. Plus vector c, which contains c1 for the first, c2 for the second, and c3 for the third. And to finish off this, we're going to find one of the definite integrals. We can do something from homework. Let's find something cute. When I say cute, I mean, partial fraction decomposition. Yeah, all of those tricks, partial fraction decomposition, they all can be completely avoided. Yeah, this is a cute one. 73. Integrate 0 to ln 2. You immediately know it's going to be nice, right? E to the t, comma, e to the t, cosine pi e to the t. It's a 2D vector. That's nice.
Getting a vector from this, right?
Well,
We should be getting a vector from this. Right?
yes. Now it's going to be a 2D vector, so your vector C will only have C1 and C2. Yes.
It's gonna sound like a dumb question, but what's the point of vector integration? Like, what does it represent?
All integration is accumulation, all of it. And if you think about it as you have functions and inverse functions, right? You have operators and their inverses. So derivative and integrals are pairs.
Yeah.
So if you want to go from position to velocity to acceleration, you would be differentiating. But if you have acceleration, then you can integrate to go back into velocity, to integrate to go back into position vector.
Does it represent anything graphically? Kind of like integration in the form of like a two-dimensional?
Well, we are going to have line integrals that will correspond to. So we are going to do, and the next chapter is going to be chapter of integration, I believe. No, 2 chapters from now. Where we're going to do 3D integration to find volume and bulk and other stuff. And then there will be line integrals, which will be coming back to this, and parametrization and so on to calculate the area of a curtain and stuff like that. So yes, they will have representation later on.
But for now, it's more of just an inverse operator for derivatives.
All right, so how do we integrate this? Any ideas? Did I copy this right? Let's first check that. Now, after everyone suffered. Yes, I got this right. So clearly, integral of e to the t is e to the t. It's the second one that it's annoying. So if we use, so here, let's do blue. Integral of e to the t cosine pi e to the t dt. What should we do? We can make u substitution, right? Equals e to the t. Then du is e to the t dt. When we plug in, we get u cosine pi u du. Now that I think of this, if I bring the pi along, then there will be a pi over here, so I can kick 1 over pi outside and not worry about pi, so I can just have cosine u du. Now, how do we integrate this? What did you try? Essential oils? No? By parts. You okay? By parts. All right, so I gotta use different letters. I can't use U and V now because U is used up. So M and N. M equals U. N equals cosine dn equals cosine u du. dm is equal to du. And n is equal to integral of cosine is sine u. So 1 over pi times u sine u minus integral of sine u du, which is 1 over pi u sine u plus cosine, no, plus 1 over pi cosine u. And u is pi e to the t. So pi and pi will cancel, so I just have e to the t sine pi e to the t plus 1 over pi cosine pi e to the t. Great. So now the problem is integrated, so we are getting vector e to the t comma e to the t sine pi e to the t plus 1 over pi cosine pi e to the t, computed from 0 to ln2. When I plug in ln2, I have e to the ln2 minus e to the 0, comma, and now this is e to the ln2 sine pi e to the ln2 plus 1 over pi cosine pi e to the ln2 minus, now I plug in 0, it's going to be e to the 0 sine pi e to the 0, and then minus 1 over pi cosine pi e to the 0. E to the ln2 is 2, so I get 2 minus 1, comma, 2 times sine 2 pi plus 1 over pi cosine 2 pi minus e to the 0 is 1, so it's just sine of pi minus 1 over pi cosine pi 2, comma, so all of the terms with sine and pi die, and I have cosine of 2 pi is 1, so this is 1 over pi plus negative 1 over pi to 0.
That's 1 0.
What happened?
2 minus 1 is 2.
Of course, 2 minus 1 is 1. Please pay attention. It's clearly 1. Because 2 minus 1. Thank you. So 1 0. Cool, huh? Another one? We have time. One more, huh? Why not? What else?
Another cute one.
How about another tangent line?
I'll take that.
Let's do another tangent line because tangent lines are cute. Tangent line at t equals 4 for r, square root of 2 t plus 1 comma sine pi t comma 4. So find the tangent vector, right? That's your v. Plug in 4 over here to get your point. Put all that stuff together.
Does there sine pi t?
Yes. Does it make sense?
Yes.
Okay. Well, for tangent line, right, you have to find the derivative. So if it's not stated, it's the concept, right? But if it's stated, you just do what it said. So for the tangent line, the process is always to find the derivative, right? So R prime is going to be 1 over 2, no 2 will cancel with the chain rule, so just 2t plus 1. This is pi cosine pi t, and then at 0. And we can just plug in 4 for vector v. It's any vector in that direction, so whether it's scaled or not scaled, it doesn't matter. So when we plug in 4, vector v is equal to r prime at 4. There we go. So that's going to be 1 over 3. Cosine of 4 is 1, so that's pi. And this is a 0. So we have our vector v. And then to get the point, r computed at 4 is going to give us a vector 3, 0, 4, which will give us a point 3, 0, 4. And now we're going to have x, y, z as 3, 0, 4 plus 1/3 t plus pi t plus 0 t. So the tangent line is at 3 plus 1/3 t, pi t, and 4. And then you celebrate. Oh. It's important. You know, small victories.
You should bring in those after the test,
After the test? Why?
so we can celebrate. Small victories.
These are not gonna make it. It's just tonight.
You bake them. You bake them.
I see I've been cut off by the authorities.
No, I'm just giving you this back so you can wrap it up.
Any questions, concerns about vector valued functions and calculus? No? See you tomorrow.